Okay. This talk has one problem, one algorithm that I want to describe and outline the analysis of. Two facts about polynomials that were new to me, univariate polynomials, and one open problem and one open meta problem. Okay. So if I will star the slides where this shows up, the problem, the algorithm, the two facts, and the open problem. At the rest of the time, you're welcome to check your email or whatever else you want to do. Or do something more useful. Okay, so the problem is independent component analysis. Problem model, independent component analysis. It falls under what we now call unsupervised learning. So there's data that's generated from some model. In this case, a probabilistic model that I'll describe in a second. And the model has some latent structure, and your algorithmic problem is to recover that structure. It originated in signal processing, and the earliest reference I know is by Newton and Hérault in 1989. And this is how they describe the problem. So here's the problem. Here's your first star. You have points in n-dimensional space, x1 vectors. That's the data. And the model is that each x comes from a linear transformation of another vector s, which is possibly in a higher dimensional space. With the assumption that the coordinates of S are independent. They're generated from independent distributions. Okay, so S is coming from a product distribution. The distributions for the SIs could be different, but when S is generated, each coordinate is picked independently. The matrix A is unknown. And that's the model. So you're getting IID points x1, x2 generated by a linear transformation applied to a product distribution. And your goal is estimate A. Therefore, the basis of the product distribution that's unknown. Somehow there is for x a special basis, the latent basis. That's the one in which the product distribution on the SIs is revealed, and your goal is just to recover that. Okay. Now, estimate A in what sense? So you'd like to estimate, let's say, the columns of A, but you can only do that up to scaling, because scaling A and scaling down the coordinates of S is effectively the same thing. So estimate columns of A up to scaling and an error of epsilon. So that's the problem. I guess the first thing you could ask is this well defined? Meaning, given data that satisfies these assumptions, is the matrix A essentially unique? And the answer is no. For example, if the S comes from is drawn from a Gaussian, because then any A that's orthonormal, any rotation is the same. So it's not unique. It's unique up to rotations only. So we cannot avoid Gaussian. So we make one additional assumption, which is that at most one SI is Gaussian. And the others are different from Gaussian in some way. And we'll have to make that precise for an algorithm. But every other coordinate is different from Gaussian in some way. So useful example to keep in mind might be, suppose you see a sample of points and you're told that they come from a sample of points, and you're told that they come from parallelepiped. Okay, so right, so there's some parallelepiped, and the sample comes from there. You just see the sample, and you want to recover the parallelepiped. Yeah, that's one example. Yes.
So you know the distribution of S?
No. You only know that it's a product distribution. And it's all but one. Yeah, so this is precisely the set of assumptions. I guess this is 1, this is 2. Okay. So in other words, you would like to in this case there is a natural transformation, right? It's the transformation A just corresponds to the transformation that you would have applied from a cube, from an axis aligned cube that maps it to this picture. So your goal to answer this problem is to estimate this transformation that would have taken samples from a cube to the samples that you see, if you assume it's a parallelepiped. Okay. So, I mean, in any case, the goal is to find this latent basis. Sort of the most well-known algorithm, basis finding algorithm, is principal component analysis, or the eigenbasis. Right? So, SVD. So you could say, how about PCA? What will that do? Right? By that I just mean compute the eigenvectors of, let's say, the covariance matrix of this data. Take the covariance matrix and compute the eigenvectors. What will that do? So in the case when the parallelepiped is axis aligned to begin with, and the axis lengths are distinct, right? Sorry, it doesn't have to be axis aligned, but if the axis lengths are distinct and it's a cuboid, it's an orthogonal parallelepiped, it's a cuboid and the axis lengths are distinct, then PCA will find it. Rotation doesn't matter. The largest eigenvector will be the one corresponding to the longest axis, and then the next orthogonal one, and so on. PCA will find it. But in any other case, no. Okay, so you can find rotations of a box, but that's about it with PCA. Okay, so in general, no. So here is an algorithm that was proposed and analyzed by Fries, Jerem, and Cunnan in '96. It was actually proposed in the ICA literature earlier. There's a huge literature on this. There are a couple of books and many algorithms, very interesting algorithms with implementations. So here's what they said. So step 1, make your sample isotropic. And that just means that you compute the mean and the covariance matrix of the sample, and then you apply a linear transformation so that these become the 0 and the identity. Okay, so after this step, we have the expectation of x is 0, and the expectation of xx transpose is identity. And of course, at this point, it's completely clear that PCA is useless, because the eigenbasis is any basis. Okay, so then they said, let's compute the local optima of the function f of u equals expectation of u transpose x to the power of 4, where u is in the same dimension as x. So u belongs to, let's say it's a unit vector. So u is in the sphere. Okay. So unit vectors. Over unit vectors, find local optima of the function f of u. So in general, this function is hard to maximize or minimize, but over the sphere. But because we're talking about local optima, in principle, you could do some kind of gradient descent and get an approximate local optima. You still have to worry about number of steps and so on, but they did that. Now you can ask, what should this do? What will it do? What happened after the first step? So let's analyze this. After the first step, you start with some parallelepiped, right? That's your distribution. and you made it isotropic, which means you will get a cube, but the cube is in some arbitrary rotation. And now the problem is to figure out the rotation. Okay? And their claim is that the local optima of this function are precisely the axes of the cube. So once you have them, you know the rotation.
I didn't follow the function.
It's the expectation over the input distribution of u transpose x to the power of 4, the fourth moment, along the direction u.
So you don't know the input distribution.
But you have samples from it.
You have one sample.
You have access to IID samples. So the complexity of the algorithm will be measured by the number of samples it uses and the additional arithmetic operations. Okay, so by doing this step, they're getting it to a cube. Now the question is, what's the rotation? And the algorithm is find the local maxima of this. Okay, so it's actually, so let's see what this looks like. It's the expectation of the sum of j going from 1 to... Now here, since we're talking about inverting here, we've assumed at this point that m equals n, and a is full dimensional, so it's non-singular. The smallest singular value of a is greater than 0. Otherwise, this doesn't make sense. You cannot make it isotropic and so on. So we made this additional assumption at this point. Okay, so what is this function? Summation of uj xj to the 4. Let's do it. So, there's going to be 4 terms. So maybe I call them I, j, k, l, since it's only 4. And then there's the expectation of xi, xj, xk, xl, and ui, uj, uk, ul. Right? Now, this will be 0 unless the powers of x are even. Right? So all the powers of 1, powers of 3 vanish. Only the others survive. So what are you left with? Summation over I, expectation of xi to the 4th, ui to the 4th, and then 3 copies of summation of I not equal to j, expectation of xi squared, because everything else has an odd power. Ui squared. Right. Now you see, this is almost a square, right? This is almost a square. So let's complete the square and put in the other term here. Okay, so you get here summation of I, expectation of xi to the 4th minus 3 times expectation of xi squared, xj squared, ui, xi squared. Ui to the 4th plus 3 times summation of whole quantity squared. Okay. So this has all the terms for I not equal to j. I added in the term for I equal to j and subtracted the term for I equal to j. That's all. Now this is a constant. This is just 3. Because the expectation of xi squared, because of the isotropy assumption, is 1. And u is a unit vector, so this is 1, so that's 3. This term is just 3, constant. And really you're finding the local maxima of this. Okay. Now, the local maxima of this will precisely be, the EIs, if the transformation was identity. But the point here is that this is non-zero if expectation of xi to the 4 is not equal to 3, and 3 is the 4th moment of the Gaussian. So under the assumption, so the additional assumption now is that if the 4th moment of your distribution, and I'll get to general distribution in a second, is not equal to 3, then a local optima find the axis of the cube, are the axis of the cube. I implicitly used here that, okay, let's assume that the A is identity because it makes no difference to this transformation. But in recent work over the past now 6-7 years, Sham and many co-authors have written this in, I think, a more transparent and easier to manipulate way. So let's go back to this fourth moment here, expectation of U transpose X to the 4, and think of it as a tensor applied to the vector U. So again, we have this expansion here, but really that's just like taking X, tensor product with X 4 times, taking this expectation, that's some tensor once you take the expectation, it's an entry-wise expectation, and you apply this tensor to the vectors U, 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 U. Right? So that's a polynomial here, and you're applying it to the vectors U, U, U. So this is just another way of writing this. And the point is that when X equals A times S, right, and we know already that S is isotropic, so you get here that this is the same as the sum over I going from 1 to n, the outer product, the fourth order product of each column vector applied to U, U, U. And now let's forget about the U part. Let's just look at the tensor, which is this expectation, and that's what we would like to write down. Yeah. So let me put that in a separate equation. So so another way to write the same thing is that if you look at the expectation of the fourth tensor generated from X, so this is outer product of X, 4 copies of X, and take the expectation, and you subtract from it 3 copies of the outer product of X with X, take the expectation, and you have to do this times its transpose, so then this is exactly equal to the sum over all the columns of A of the outer product of each column times this coefficient that we just computed, which is expectation of Si to the 4 minus 3. Okay, this is the same thing that I did explicitly, but written now as a tensor equation. And taking out taking U out of the picture. So we're able to calculate this tensor because we have samples X. You can estimate this n to the 4 entries at most. Estimate this. This we already made it isotropic, so this is the identity. Cross the identity is giving us a sum of outer products of the columns that we're after. That's what you want to estimate. So now the problem is not a eigen decomposition like PCA, where you would here have coefficients lambda I times eigenvectors outer product twice. Now you have fourth order products of column vectors. And can you find this? So what they showed is it's basically the same algorithm, local search. But what they showed is that as long as the AI are orthogonal, assuming the AI are orthogonal, which they are once you make it isotropic, then a simple tensor power iteration, which looks just like an eigenvalue power iteration, but it's, let me write it down if you haven't seen it. We will see this in a couple of talks in the workshop in more detail. If you have a fourth order tensor like we have here, then the update is just x goes to t of x, x, x. So applied 3 times, that gives you a vector. That's your update, and you might normalize by its length. An eigenvector update for a symmetric matrix would just be x goes to ax. This is the tensor power iteration. And this converges very fast, actually, faster than what it does in the second order. Does not need the distinctness of these coefficients. The coefficients could all be identical. They just need to be non-zero. But it does need that the AIS are orthogonal. Okay. And of course, that means that you can't have more than n of them. So as long as you have n orthogonal vectors, or your original matrix is something that's non-singular, it's simple, it's local search works. Several papers giving faster convergence times for this specific case. And when you put it in this setting, it also works for any product distribution, but there is the assumption that this fourth moment of each product distribution, each component of the product distribution is different from 3. It's different from the Gaussian. So this leads to two questions. One is, okay, you can have lots of distributions that look like the Gaussian both in the second moment and the fourth moment, and the sixth and eighth and so on. Can you solve this general problem? And second, what if the number of components is actually more than the dimension? So you're actually starting with a parallelepiped in a very high dimensional space, and what you see is only a projection. You only see samples in a projection. So your matrix, your vectors X, are generated by a long matrix multiplying a product distribution here. In this case, this method cannot work because you cannot have orthogonality of the columns. You can have orthogonality of at most n columns. And so these are two things. So now, we talked about two ways. One way in which you're different from a Gaussian, the fourth moment is different. So now here is a general way in which any distribution that's not Gaussian must be different from a Gaussian. And so for this I introduce or remind you of some functions. So let's call phi of u to be e to the expectation of I u transpose x. U again is the vector in Rn, the same dimension as x. For now, let's keep everything in the same dimension, so m equals n, but we'll generalize that in a minute. Okay, so it's like the moment generating function, but it's over. It's complex, yeah. And the characteristic function, right? And now let's look at the log of this, which of course splits into the sum here. Just call the ith component. And it actually splits into this part also because it's a product distribution on the u's. On the x. Okay, now the way we'll talk about being different from a Gaussian is through the cumulants. If you haven't seen them, the cumulants are, the kth cumulant is a polynomial of the first k moments. And precisely which polynomial is, you can see by, so let's take a one-dimensional case. It's just write down this second characteristic function as a generating, as a polynomial, basically Taylor approximation. And so if I do it for one-dimensional variables, let's say the variable z evaluated at a point t, then I can write it as a sum cumulant, the jth cumulant times so these are the cumulants. Now the first one will be the mean, the cumulant 1 will be the mean, cumulant 2 will be the variance, and then fourth cumulant is exactly what we have here, and so on. Now for a Gaussian, all cumulants except the first two are 0. So for x drawn from n01, cumulant k of x is 0 for k greater than 2. And even more, a classical theorem is that, by Marcinkiewicz, we found out, is that the only distribution for which has a finite number of non-zero cumulants is the Gaussian. So any distribution that's not Gaussian has to differ from the Gaussian by having a positive cumulant that's bigger than 2. You'll see it. So the fourth moment assumption was the simplest one you could make, given this was symmetric, but it could be different at some cumulant, the kth cumulant, which is a polynomial of the first k moments. Okay. Fine. So this is how we'll measure. So we will assume only that there exists a k such that the kth cumulant of each component distribution, right, is positive. And I'll give it a value delta. Think of this as a constant, right? Instead of 4, it's some other constant. Okay. And now, under this assumption, here is the algorithm. Under this parameters, here's the algorithm. So this is the second star algorithm, Fourier PCA. So the first step will look pretty similar. Make the sample isotropic. Make sample isotropic. So that we now have expectation of x is 0 and expectation of xx transpose is the identity. And this effectively means that A is a rotation. The second step is here's what you do. You're going to compute a weight for each point of each sample point. And so you have these sample points x1, x2, and so on. Here are the weights. The weight for a point x is just e to the I. It's a complex weight, u transpose x. Now we have to pick a u. I'll tell you in a second how we'll pick u, but we'll pick it from a Gaussian. So u will be a random vector. So it's like a random Fourier coefficient. But we'll normalize it so that this sum is easier to express over all the points in your sample. That's the weight. Then, subject to these weights, compute the mean. I'll call mu u, since u is the special number, which is just expectation of x times w of x for the sample. So average this over the sample. And compute the covariance. Let's call it sigma u. The expectation of, actually, it's more convenient to do ix. And then I squared will become minus 1 here, so minus x transpose wx. So it's just the mean and the covariance, as you normally would do, but it's with these weights. And yeah, and now step 3, output the eigenvectors of sigma u. And that's the algorithm. So it's PCA, but it's PCA applied to this reweighted covariance matrix, where the weights are complex exponentials. Now because I put the I there, the only reason we have this I here is because this is always bounded. If I did it without the I, depending on the distribution of x, it might not exist. With the I there, the absolute value is at most 1, always exists, no problem. So this is the algorithm. And let's see why it makes sense.
So you're saying the columns of A are going to be decided?
Exactly, yes. Eigenvectors, the final theorem is that the eigenvectors will be approximations to the columns of A. The matching we have to do, which one is which, but they will be the after. And the sample size. Okay, so to complete the theorem statement, at least informally, the output will be will approximate AI, and the number of samples will be polynomial in n. So really it depends on this k. For where the cumulant is different, it's n to the k squared, 1 over sigma n of A to the k. You also need the original matrix vectors to be somewhat far apart. 1 over delta to the k, and so on. So if k is constant, everything is polynomial. But you don't need to know it in advance what the k is. Excellent. Okay, so I tried to explain why this works with basically two equations. And that is that you take this function, I said the second characteristic function, and let's look at its derivatives. Right? This is a vector, a function of a vector. So this first derivative will be, you have this in the denominator, and then phi of u is the expectation. So the expectation stays, and I get ix e to the I u transpose x. Right? This looks very much like this mean here. Right? Here is the weight, here is the mean. So the first derivative, which is a vector now, right? X is a vector. By this I just mean the vector of the partial derivatives, is exactly this empirical, is the limit of this empirical mean we computed. Now let's look at the second vector. The second derivative is Hessian, and I can do the calculus, but okay. So we get two terms, right? Take the derivative of the ix transpose e to the I u transpose x. The derivative is with respect to u, so the x's don't matter, and then minus. Okay, so this is the second moment minus the first moment squared, which is, you can rewrite as the covariance. So at least what we're computing, so all I've shown so far is what we're computing is the Hessian of this second characteristic function. But why should this give us what we want? So that's the next equation, which is again also very simple. The lemma is that this covariance matrix is equal to A times a diagonal matrix, which I'll specify in a second, times A transpose. And the diagonal matrix will have as diagonal entries the same second derivative function, but applied to each individual coordinate of the unknown product distribution SI. So it's the psi I double prime applied at the point A transpose u of I as a one-dimensional function. So what is that? Let's just write it explicitly. This is just the second derivative of the, or let's do it like this. It's the expectation of SI squared e to the I u transpose AI SI, or let maybe call it J here to avoid confusion, divided by minus the, so let me just say it's the reweighted covariance of the SI. It's the covariance of Sj under the weighting e to the I u transpose A. So you've got this Hessian looking like the matrix A that you care about, a diagonal matrix with complex numbers on its diagonal, times this matrix transpose. The matrix, remember, after the isotropic transformation is orthogonal, so the eigenvectors of this are precisely A, the columns of A. Okay. Now, remember that we had a problem with PCA in the first place. It only finds it correctly if the lengths are distinct, if the eigenvalues are distinct. Otherwise, there's no, it's not uniquely defined. So what we need here is that these second derivatives, now they're coordinate-wise second derivatives, they're just one-dimensional, should be distinct. Why should they be distinct? And what are they? So they are, no, we know exactly what they are. They are of this form, second derivative of this. If we take the second derivative of this, we get another expression in terms of the cumulants. and a polynomial in terms of the cumulants. And then what we do is we know that one of the cumulants, let's say the fourth cumulant in that case, is greater than 0. But there is a point where there's a cumulant that's greater than 0. That's the k. We truncate the approximation, that this series at that point. We're going to make sure that the rest of the terms have very small error. The reason we can do that is because they have higher powers of t. So therefore, by controlling the variance of this Gaussian from which we're picking u, we can make them arbitrarily smaller than the first k terms. And then, but then there's the question, you've got now degree k polynomials. And you need to show that these degree k polynomials, when evaluated on independent random points drawn from a Gaussian, are going to be far from each other, because those are the gaps in the eigenvalues. So this leads to fact number 1 about polynomials. And they are one-dimensional, because these polynomials are just in this one-dimensional SI. I've given you a family of polynomials, P1 at P1, P2 at Z2, and so on. And these are of degree k. And you'd like to know that just because the p's are arbitrary, and you know something about their coefficients, the coefficients are this delta, you'd like to show that just because the z's are independent, the values of these polynomials are actually far from each other. It's an anti-concentration. So it's this polynomial anti-concentration. And let me just state that lemma. Let's do it for a single polynomial, and it won't make any difference. So let's take a polynomial px of degree k, and it's monic. So that just means the largest coefficient is, the leading coefficient is at most 1. And then for any epsilon that's in between 0 and 1, and for any t, the probability when you pick z from a Gaussian, 0 sigma squared, that the value of the polynomial is close to t, closer than epsilon to t. Right? So this is the probability that your polynomial is concentrating in an interval of width epsilon in its value, is smaller than a constant times k times epsilon to the 1 over k divided by sigma. That's the power. So as you make sigma smaller, the variance of the Gaussian smaller, this probability goes up because everything is getting concentrated. And as you make the interval bigger, this probability also goes up because you have a wider interval to do this. I won't do the proof of this, but it's actually just one lemma, and we can point out the extremal polynomial px for which this is true. But given this type of dependence here, we see that we'll need to set sigma to some power of k, and that's what gives the claimed complexity of sound. Okay, now the two stories I wanted to tell, I won't have time for both or most of both. One is what happens when m is much bigger than n. So this picture where you're trying to recover many columns, even though you're only seeing signals in low dimensional space. And for this, the solution it can be said in one sentence, which is that we just consider higher derivative tensors. So instead of the citation, go to the third derivative tensor, fourth tensor, fifth tensor, as much as you need to go, depending on how large m is. And you go up to the point where the columns of m, if you thought of them as powered up vectors, are linearly independent. So that didn't make any sense. If you take the vectors, let's say 1, 0, 0, 1, and 1, 1, I mean, that's not linearly independent. But let me take each column and take each column here, multiply it with itself, and write it as a vector. So then it goes to 1, 0, 0, 0, 0, 0, 0, 1, and 1, 1, 1, 1. And now they're linearly independent. And you can do this for any matrix. As long as you have distinct columns, if you power up the columns, there will be a power at which they all become linearly independent. Whatever that power is, that's the m, that's the power to which you need to take the derivative. And when you do that, you get a very similar equation like this, except it's with tensors, and you can recover the tensors. So that's one side of the story. The other side, which is really what I want to talk to you about, is that, okay, so this was joint work with Naveen Goel and Ying Zhao. And Ying is an expert coder also. So he decided to implement this. I mean, it looks like PCA. You have routines available for PCA that handle precision and so on. So he implemented it. It doesn't work even for n equal to 10. I mean, you need 10 to the 10,000 samples to get any decent thing. It's some sense not surprising. You know, there is this exponential n to the k squared and so on. So it said, okay, I mean, we should be able to do this at least for some size. So we went back to the algorithm, and this is more or less the last thing I'll describe. And we made the following change. You see, the analysis here relied on all the gaps of the eigenvalues being distinct. You need that. Otherwise, you might not capture an eigenvalue. You're trying to get the eigenbases in one shot. You need all the eigenvalues to be distinct. You need those polynomials to all have distinct values. Okay. What if, instead of looking for all eigenvalues to be distinct, we just want to find one gap? So you order your eigenvalues. Okay. Assume for a second these are real. And I look at the largest gap. This gives me a subspace. This gives me a subspace. Partition to these subspaces, project, recurse. That's the algorithm. Recursive Fourier PCA. So you're going to do this part. And then, instead of outputting the eigenvectors, you we only look at the real part of sigma, find largest gap in eigenvalues of the real part of sigma u. And then that gives you a subspace partition v1, v2. Recurse on v1 and v2. By that, what does that mean? Take the sample, project to the v1, apply this algorithm again till you're down to one-dimensional spaces. Do the same thing on v2. And then this will give back some subspaces. You return those, give back transformations. You return those transformations concatenated. That's the output. Okay. Now you can ask, how different is max from min? Previously we needed the min gap to be small, to be large. Now we only need the max gap to be large. Okay, so let me just do a toy example to conclude the talk. Let's take two distributions. Distribution number 1 will be uniform over the interval 0, 1. Distribution number 2 will be the Gaussian. And I pick endpoints from the interval 0 to 1. I'm interested actually in a polynomial on these points. But let's assume we're just talking about the points themselves. P of x equals x. Then if I pick n random points here, well, the min gap is like 1 over n squared. Because, you know, each point, you're picking n other points roughly. So fix the first n over 2 points and take the other n over 2. One of them will be within 1 over n of one of these. Okay? So the min gap is like 1 over n squared. And the max gap is like log n over n. So this looks interesting. This would improve the exponents there by a factor of 2, but it's not going to speed up the factor. Now let's look at what happens if you had a Gaussian distribution. Same thing, but with the Gaussian. Let's say the standard Gaussian. I'm picking n points and I'm asking what's the min gap and the max gap. The min gap is about the same, right? Because there is this interval in the middle which will capture half the points, and your min gap will still be like 1 over n squared. But what about the max gap? The max gap, you're going to look at the point where, let's say, you have a 1 over n chance of being this side, tail, and then look at the point where you have 1 over 2n chance of being in the tail. And now you actually have a constant probability of picking one point here and all the other points here. And you see this gap. And this gap is like root 2 log 2n minus root 2 log n, which is roughly 1 over root log n. The gap is not linear in n, it's only polylogarithmic. And when you recurse, actually the total number of samples you need is O tilde n. Even when you use polynomials of degree 2, which is what we're doing in the full dimensional case. So if you go to polynomials of degree 2, then this max gap remains polylogarithmic, 1 over polylogarithmic. If you go to polynomials of degree 3, the gap becomes 1 over n to the 0.6. So it doesn't work. But if you go back, but degree 2 already is interesting because that corresponds to the fourth moment assumption. So under this fourth moment assumption, you can actually do ICA with nearly linear number of samples using PCA recursively. That's the result. I guess I should state the open problems. One problem is all of these methods. So I didn't spend any time on the underdetermined case. That's probably mathematically the most interesting one when m is much bigger than n. What if your observation is just one-dimensional? So your matrix looks like this, and you're just seeing one-dimensional observations. So you've got your parallelepiped, and somebody's projecting it onto a line. Okay, you're just saying, can you figure out the parallelepiped? Okay. So let's assume it's a cube, so that, right? Can you figure out the rotation of the cube if you're given one-dimensional projections? And I don't know whether it's possible or not. And the other, I guess, a more meta question for both unsupervised, I mean for these methods in general, is what if your data actually came mostly from a model like this, but with epsilon fraction from arbitrary points, let's say in a bounded set, and then suddenly everything breaks. So the underlying algorithms for higher dimensional tensors are robust to tiny amounts of noise, enough to make it work if data actually came from the model, enough to compensate for sampling errors. But if you actually had 1% of data not fitting the model, then it's absolutely no guarantee. Okay, let's stop there.
Just quick clarification, you still need this polynomial concentration in the recursive version?
We use a different one. It's because this was for just a pair of polynomials, and you need to apply it to all pairs of the n polynomials. Now we need to look at a set of n polynomials and ask for the maximum difference between them. So that's the second fact, which I haven't stated precisely yet.
It seems like, what's nice about this algorithm, as you point out, these characteristic functions, right, they're bounded. So, but you have this exponential dependence on k,
yes,
which seems fishy because, like, suppose I just, it seems like a nice way to characterize this would be some kind of information theoretic distance between, like, a product distribution and a Gaussian, and it seems like you should be maybe exponential in that, but because this k is fictitious, like you don't need to know k here, right?
Yes. So the k. Now, if the first cumulant where you're actually non-zero, the first moment where you were different from Gaussian was the kth moment,
yeah,
then you do need exponential in k samples to tell that.
No,
but not n to the k. You need only yeah.
But like you can imagine the tails being so different to compensate for. Like it's not. Like if that moment is bounded, yes. But suppose like that, even at the kth moment, it was so different from.
But you couldn't say that.
Like put it another way, like maybe the first moment is some different. Like you could compensate if
right,
the second moment is more different, and so on. And it feels like this algorithm, the fact that it doesn't need to know k at all, suggests.
So maybe this is not the right metric to compare with a Gaussian or a product distribution.
Well, I think so. It's plausible that the algorithms are right, but you could maybe strengthen it to be something like the distance between these characteristic functions, which is more like an information theoretic quantity. Right?
Yeah, it's plausible. This
which I think is actually what's happening here, like, that you're closer to the information theoretic distance between like a product distribution.
But you do need concentration of the moments of that order, right? And for that you do need exponential in that order. I don't see how
You need concentration of the characteristic function, but that's different than getting a higher moment correct, because everything's bounded here. You can chat a little.
Yeah, sure. No, I see the point.
Like, things are bounded because you're using a character.
I mean, you can certainly come up with examples where you would need at least as much as the kth cumulant, but
point.
It's not the point.
That's not the point.
Yeah.
The point here is those are,
there is potentially a nicer way to compare these distributions, for which this still works. That's absolutely.
That's the
I
point.
agree. Yeah.
I have a question on your heuristic. So, A is unknown, right?
Yes.
Yeah. So, in the bound you have, which I can barely see, or maybe you erased.
Yes.
It's been erased. But it had sigma it said sigma n of A, but you don't know what A is.
No.
So.
You see, the point is if the original A had vectors that, it was poorly conditioned, it actually had a vector very close, then you need a lot of samples to figure that out. Yeah.
Okay, so but there's no way, you can't just cut it off at some point and just say,
Oh yeah, if you had some accuracy error in mind, sure, you can cut it off, and then you would get a lower dimensional subspace, but you'd know that whatever you missed was really very close to this, so maybe you don't care. So you would be putting very low weight on that.
The other thing I have with the algorithm, so you have this polynomial concentration and the subspace separation.
Yes.
But this log term you claim,
Yes.
you can do it with log O(n).
1 over, yeah, log n, yeah.
That's under the assumption that the separation comes in the middle, right?
Oh, no. We don't know where the separation is. In fact, the separation tends to be skewed to be at one end. So if you since we're looking at evaluations for points drawn from Gaussian, turns out that the separation comes not at points in the middle, but
I'm saying for the eigengap.
Yeah.
So you, step 3, you're looking at the eigengap
Yes.
between V1 and V2.
Right.
Right. So you get that number of iterations. The log is it? Maybe I'm.
No, this is the gap. This is the actual gap. The gap between, so the actual gap that you see between the eigenvalues, there will be a place where the gap is at least 1 over log n, it turns out.
Right, but you don't know where that is.
Oh, you can find that because you computed all the eigenvalues.
Yeah, but when you separate V1 from V2, you might get one eigenvalue on one side and minus.
No, after sorting them. By gap, I mean take the eigenvalues in sorted order, and there will be a point where the ith eigenvalue and the I plus first eigenvalue will be different by 1 over log n.
So what if I is n? Or what if what I'm saying is, what if that gap separates 1 from the rest of them?
So then the gap is between 1 and 2. So V1 would be the first eigenvector, and V2 would be the rest.
Then you have to repeat this n times if the gap comes.
That's right. You might have to repeat this n times. But you can reuse the same samples. You don't need to do more than n samples. Yeah, you might need to repeat this in the worst case order n times. Yeah.
Maybe I'm being unfair to this side, but anyway, let's and we'll come for the next talk at noon, right?